Welcome back for another installment. Today we're going to be talking about radical functions and transformations. Let us construct the graph y is equal to the square root of x using a table of values. So press pause and see where you end up. After you've graphed it, come join me. So I'm going to take a look at y is equal to the square root of x. And I'm going to pick some x values here. And if you notice, for some reason, I'm cheating my Cartesian plane to the right. So I'm just going to pick random x values. I'm going to start off with -1. 0, 1, 2, ... And this is my first failed attempt. And by the way, when x is equal to -1, when I plug in x into that, it's the square root of -1. And on the real plane, that does not exist. So this is actually not a point. And I'm going to take a different tack to this. I'm going to ask myself, what inputs of x are a perfect square? Because if I can determine what's a perfect square, I can take a square root and end up with integer coordinates. If you don't know what I mean, I'm going to take the first perfect square, 0. When x is 0, my y coordinate will be 0 by plugging it into this equation right here. The next value that I'm interested in, and the perfect square, is 1. When x is 1, the y will be the square root of 1, which is 1. I'm going to skip 2, because 2 is not a perfect square. 3, same reason. I'm going to pick 4 next. And when x is 4, y is 2. 9, 3. And what we end up with, when we graph these points, is this function. Notice how this function doesn't exist when x is negative, because you can't take the square root of a negative number. Just quickly noting some characteristics about this is my domain is x exists such that where x is, almost lied to you, where x is greater than or equal to 0 where x is element of the reals. The range is y exists such that y is greater than or equal to 0 where y is element of the reals. Put into interval notation, the domain goes from 0 to infinity, and the range goes from 0 to infinity. So that's kind of an important thing to note. Also, what's really important is the graph has an endpoint at 0, 0. So right here, there's an endpoint to it. All right, fair enough. So this is the graph that I'll be using today. I love it. All right, so let's go over here, and we're going to start graphing. And allow me to zoom in again. So let's consider the above function y is equal to the square root of x. We're going to graph y is equal to the square root of x minus 2. And I'm just going to maybe just change this ever so slightly. I'm just going to say, let's let f of x is equal to the square root of x. And we've been doing transformations for so long. So I'm going to take it underneath that lens. If f of x is equal to the square root of x, I'm going to just simply put this in brackets to let it be known, like this function can be written as y is equal to the f x minus 2. That is, h is equal to 2. So if I start off by graphing f of x is equal to the square root of x, which I will do right now, and you should be fairly well scripted in graphing this without any prompts. It's a basic fundamental graph. What I'm going to do is I'm going to graph the function, but I'm going to shift it over 2 units to the right. And that is my function, y is equal to the square root of x minus 2. Must you do this? No, you can graph this off the top of your head, but you're going to have to require some skill to get there. In other words, you're going to have to say, well, what x values will work? And when we're talking about a square root function, the radicand has to be greater than or equal to 0. And if I do that, this is my radicand. My radicand has to be positive or it can be equal to 0. And the domain that I would graph it would be x has to be greater than 2. So I let my radicand be greater than 0. And simply, in step 2, I added 2 to both sides in my inequality. So this describes the domain. And then you can make a table of values, for instance, for an x value, and you would start at 2. And then you'd probably play the game, what values of x make my radicand a perfect square? 3, and then I believe 6. And then you would have the outputs 0, 1, and 2 for y. But we're going to be focusing on transformations. And if you're wondering why I'm going to be focusing on transformations, I believe that's the topic of this lesson. All right, next. Now, I know how to graph y is equal to the square root of x. And if I simply call f of x is equal to the square root of x, if I define a parent function as the square root function, take a look at y. Well, y is just my parent function shifted up 1 unit, where k is equal to 1. So here's my parent function. I'm just going to quickly sketch that out. There you are. A nice curve at the beginning. There it is. And now I am just going to shift this up 1 unit. And I have graphed 2 radical functions.